Let us talk about the root and ratio tests. So let's write them as theorems. So the first one, the root test for convergence of a series, okay, looks at the quantity lim sub as n tends to infinity of the square root of n absolute value of an. And then there are three cases. If alpha is less than 1, the sum of the an converges. If alpha is bigger than 1, the series diverges. And if alpha equals 1, then the test is inconclusive. Okay, so in that case, we don't get any information from the test. Okay, and we have, similarly, we have the ratio test, which is also for series. And in this case, what we are going to look at is the ratio of two consecutive terms. So in this case, the series converges if the lim sub of the quotient between an plus 1 and an in absolute value is less than 1, okay? And it diverges if this ratio, n plus 1 over n, is bigger or equal than 1 for all n bigger or equal than some n0, which is some fixed integer. Okay. Here, notice that in particular, if the ratio, the limit is equal to 1, also we can draw no information. Okay, so if the limit as n tends to infinity of an plus 1 over an is exactly 1, the test is inconclusive. Okay. What do we mean when we say inconclusive? So for example, we can look at the sum, the series 1 over n equal 1 to infinity, and which we know is divergent by p series, and the sum of the reciprocals of the squares, which is convergent also by p series. Okay, but when we look at, let's call an 1 over n, and let's call bn 1 over n squared. If we look at, let's say, well, these are actually examples for both the ratio and the root test, but let's do the ratio test first. So we can look at an plus 1 over an, which is 1 over n plus 1 over 1 over n over n plus 1. This converges to 1 as n tends to infinity. Okay, and we can also see that bn plus 1 over bn is 1 over n plus 1 squared over 1 over n squared. That is n over n plus 1 squared as n tends to infinity also converges to 1. Okay, so what do we see here? This is the same case. Okay, the ratio converges to 1. In one case, the series is divergent, in the other one is convergent. So that's what we mean by the test is inconclusive. Okay, we can also see, we take the nth root of an. Okay, this is 1 over n to the power 1 over n, which we can write as the exponential of the logarithm. This is the natural logarithm. Okay, But I prefer to write log instead of ln because otherwise there are too many n's around. So this is 1 over n logarithm of 1 over n. You can write this down carefully. 1 over n times the logarithm of 1 minus the logarithm of n. So we get minus log n over n. And here you can use L'Hopital or just realize that the logarithm grows slower than any power. So the limit as n tends to infinity of the log n over n is going to be equal to 0. Okay, so this is the exponential of 0, which is 1. Okay, so again is the inconclusive case. But then if we do for Bn, we'll have 1 over n squared to the power 1 over n, same trick. There are multiple ways to do this limit, but I chose this one in particular because it's very clear, right? So exponential of 1 over n, the logarithm of 1 over n squared, this is n to the negative 2. So we can just write the exponential of negative 2 log n over n. And we see the same limit as before, goes to 0, log n over n as n tends to infinity. So again, we get 1. Okay, so notice that for these two series, we are falling on the inconclusive case for both tests, but one of them is convergent, the other one is divergent. Okay, so that's what we mean when we say the test is inconclusive. All right, so let's give a proof of the two theorems. So proof, this is the root test. Okay, so for the root test, we are going to call the quantity that is involved. If we go back to the statement, we see that we have the lim sup of the square, of the nth root of the absolute value of an. That is the quantity that matters. So let's just call it alpha. Okay. And let's see case by case. So first, if alpha is less than 1, what happens? Here we are saying the lim sup. So here we have 1 and we have our alpha, which is the lim sup. That means that even if the sequence has multiple accumulation points, the alpha is the largest. Okay. So what we find is that there must exist some number beta less than 1 and some number n bigger than 0 such that the square, I keep saying the square root, the nth root of an is less than beta for all n bigger or equal than capital N. Okay, this is by the definition of lim sup. Okay, but once we do this, that means that an is smaller than beta to the power n. Okay. But now if we look at this series with this term here, the sum of the an less or equal than the sum of the absolute values of the an less than the sum of the beta n. Okay, so we can compare our original series with the geometric series with general term beta less than 1. Okay, because it's less than 1, we know it's convergent. And by comparison, the original series is convergent too. Okay, notice the comparison always, if you want to show that something is convergent, you need to bound from above by something that converges. Okay, here it's very important that beta is less than 1. All right. Notice just a small detail. We needed to introduce beta because we needed something here that was strictly less than 1. Okay, it wouldn't, beta equal 1 wouldn't work because the sum of 1 infinitely many times is not finite. Okay, that's the reason why we introduced the beta. Now, for alpha bigger than 1, the proof is actually very straightforward because it's almost by definition of the lim sup, right? Because this means if the lim sup is bigger than 1, okay, that means that there exists some subsequence nk such that the nth root, well, the nk root of a and k, that particular subsequence, converges to alpha, which is bigger than 1. And if there is a subsequence that converges to something bigger than 1, then it's impossible, okay? It's impossible that the limit of an is 0. Okay, we have an bigger than 1 for infinitely many values. And this means an cannot converge to 0. And this was a basic condition for the series to converge. So the series diverges. We have called this the divergence test. Okay, and then the case alpha equal 1, we have already covered this one. We gave examples. Okay, one that diverges, one that converges. Okay, the first diverges, the second one converges, and both of them have alpha equal to 1. So the test is inconclusive in this case, and we are done with the proof. Okay, it's very nice actually. If you notice the proof, it's based on comparison with a geometric series, which I think is very cool. It's because the geometric series is like the first one we see, and it looks like it's not going to be so useful anyway, but it turns out very useful because then these tests, we are going to use them for power series. Okay. And that was the root test, and we need to prove the, yeah, let's prove it here, the ratio test. Okay. And in this case, it's very similar. Here we have the lim sup as n tends to infinity. And here the argument, pay attention because this is very useful. Also, we will use this in later videos, the same argument. Okay, we know that the lim sup of the quotient of the ratio is less than 1. That means that because it's less than 1, what did we see in the previous proof? There exists beta less than 1 and n positive such that an plus 1 over an is less than beta for all n bigger or equal than capital N. Here I'm saying less than beta. Probably it would be still good if I put less or equal. Okay, but let's keep it with less. So this means an plus 1 less than beta an, okay, and this is for all n bigger or equal than n. So in particular, we can say, well, a capital N plus 1 is less than beta an. A capital N plus 2 less than beta an plus 1. A n plus 3 less than beta an plus 2, and so on, right? But notice here that I can apply the previous inequality every time, okay? So for example, an plus 2 becomes less than beta square an, and then an3 becomes less than beta 3 an, and you see, n plus 3, beta 3. So we have an plus p less than, well, same argument, beta to the power p an. Okay, and this is for any p bigger or equal than 0, than 1 actually. There we go. All right, so once we know this, notice what happens here. This an is fixed, okay? So now we have the sum of an from n equal n to infinity. Okay, when we look at this is the tail of the series, it's just all the terms from capital N onwards. So we are leaving out a finite number of terms. That's not going to affect the convergence, okay? Even if it's a billion billions, it's just a finite number of terms, it doesn't matter, okay? What matters is the tail. The tail of the sequence of the series is always what matters. So this is less or equal, triangular inequality, an, okay, but then I can write this the sum, let's write n plus p, okay, and then p goes from 0 to infinity. Okay, it's the same thing, but I'm writing it in a way that I can use the identity that the inequality here, okay? So I can bound this sum p equals 0 to infinity, and here I have beta to the power p an. Okay, and when p is equal to 0, on the first here I have an, and here too, so that one is equal, and then the rest I have the inequality. So we good. This term, now here's the magic. This is the argument that we are going to keep using. Now this term an becomes fixed. Okay, so it doesn't depend on p, so I can pull it out, and I get something, a constant times a convergent series. Because this is a geometric series and we said beta is less than 1. Okay, so this is a convergent geometric series. And here it's very important that beta is less than 1. Okay, so this is convergent, and therefore the original series is also convergent. Here I wrote the tail, but I mean from n equal 1 to infinity, also convergent. Okay, that proves the first part. And then for the second part, again, this one is almost obvious. So if the limit of these quotients, actually these quotients are bigger or equal than 1 from some index onwards, okay, for some fixed and 0, okay, this comes to say that an plus 1 is bigger or equal than an in absolute value for all n bigger or equal than n0. And then from here we conclude that an cannot go to 0. Okay? I mean, the only possibility would be that an is always 0. And in that case, well, that's a silly case. We wouldn't really have a series. Okay, it would be 0 plus 0 plus 0. That doesn't make, it's not interesting. So that's it. In this case, the series diverges. And then again, the inconclusive case is just as before, the same examples.